molecule for whether something is D or L is going to be glyceraldehyde. Glyceraldehyde is your simplest saccharide, monosaccharide, and it is one you're going to need to kind of know the structure of. And I've got two molecules here of glyceraldehyde. Glyceraldehyde is an aldose. It's a triose. It's an aldotriose. 3 carbons with an aldehyde at the top. These are glyceraldehyde. And one of them is D and one of them is L. And I'm going to show you that these two are not superimposable. Now, if I ignored all of that, and I brought the bottom over here, I can say, oh, look at this. I can superimpose the CH2OHs on each other. This is the bottom of the molecule, CH2OH. There's your 2 hydrogens. There's your oxygen and your hydrogen and your carbon. All superimposable. There's no problem there. I can come up at the top and I can superimpose that carbon and that oxygen and that hydrogen on each other. No problem there. They're superimposable. The problem comes in this middle carbon. And why? This middle carbon has 4 things on it. What are they? A hydrogen. Let's just look at one. This carbon has a hydrogen. It has an OH group. It has an aldehyde group. And it has a CH2OH group on it. Those are all 4 different things. That is what gives rise to optical isomers. When you have a carbon like this that has 4 different things on it, now look, come on over here. I take this molecule, I got the aldehyde at the top, that's superimposable on itself. I've got the CH2OH, it's superimposable on itself, but look at the hydrogen falls on the OH falls on the hydrogen. The middle carbons, the stuff that's on there, are not jiving. With me? So these are 2 different molecules. One's D and one's L. And we're going to figure out now which one is D and which one is L. And then we're going to compare the bottom of your glucose to D-glyceraldehyde and figure out whether your glucose is D-glucose or L-glucose. These are our reference molecules. So what does D and L-glyceraldehyde look like? What makes an optical isomer? A chiral carbon. Chiral carbon. Chirality has to do with a carbon with 4 different things on it. The 2 isomers is a pair of enantiomers. Enantiomers are optical isomers of one another. Where's my D? Okay, so Fisher was a guy that said, okay, how do we, that's kind of a subtle difference. You know, I mean, if people just randomly drew these molecules and say, how do I draw this? And so I tell someone what isomer of glyceraldehyde I was working with. So what Fisher came up with was a protocol, a standard way of drawing these on paper. And now look at this, is a 3-dimensional molecule. But what Fisher said is, okay, let's arrange it. Let's arrange it with the aldehyde. This is erythrose, but with the aldehyde at the top, the CH2 at the bottom, and the carbon chain in a vertical position. So the carbon chain is vertical. And it is fading away from you. The things that are on this chiral carbon are horizontal and they're coming towards you. So what Fisher said is, with it like that, flatten the molecule out into a two-dimensional array. So what I have here, I've got a carbon, I've got a carbon, I've got a CH2OH at the bottom. There's my vertical carbons with my aldehyde at the top. And when I smash that out like that, I'm going to end up with an OH over here and a hydrogen there. And this is actually D-glyceraldehyde. Okay, that's one. That's that one. I'll get the other one here in a second. Sit there. Sit there and I'll give you a treat. Anybody have dogs? All right, so now let's take this one. Remember, this one was not superimposable on that one. So we're going to do the same thing with this one. With the aldehyde at the top. With the aldehyde at the top. CH2OH at the bottom. Now if I flatten this out into two dimensions, I got a hydrogen over here on the right. I have an OH group. Now you see Danielle, why I'm writing like this? It is attached to the oxygen, and then the hydrogen is attached to that oxygen. So it looks like this. And this is L-glyceraldehyde. L left. So look at the bottom carbon is a CH2OH group. Come up one carbon, and if you have arranged that vertically, the bottom of your glucose molecule, this is carbon number 5 for you, because it'd be 1, 2, 3, 4, 5, 6 on glucose. Your molecule is going to have a longer carbon chain. But if you get these bottom 3 vertically, and then look at that second from the bottom carbon, if the OH is on the left, it's L-glucose. If the OH is on the right, it's D-glucose. Yeah, so let's take, here's a glucose. So get this to the top, and then kind of ignore it. And then look at, here's the bottom CH2OH group. Here's the bottom 3 carbons vertically, right here. And this OH this is fading away from you. This is pointing towards you. That's on the right. So this is D-glucose. Okay? So if yours is on the left, break it off and change the hydrogen and the oxygen so that you get the OH on the right, and you'll have D-glucose. You could start asking the question on up the glucose chain, but we will just worry about that one right there for right now. You hold it like that, so that these are going away from you, and these are coming towards you. Okay. Let me take a look at your molecules. So this is up. You want to twist this like that. See? So that is on the left. And put a stiff on it. And move it over there. And you want it on the right. Here's your CH2OH.
Because you want it to be.
Yeah, yours is. tree right here, that's on the right. See that?
Is it always on the fifth one?
Get a stiff bond in there. Only use these big bonds for that. Get another stiff bond. So these are your bottom three carbons. That's on the right. That's the, I'd like to get these in there because we're going to cyclize this off later. We'll then go tomorrow.
So when you get your
You need 6 carbons. Yeah. Glucose has 6 carbons.
So you start with
That's glycerol. So, and that would be glycerol. But now you need 3 more carbons. You need 3 more. Okay, I didn't. I do want these ones here, but I want.
I thought it was cute. Or no.
And when it cyclizes. But, so what is this? This D or? Well, it is flat. These are fading away from you. This is horizontal. And what side of that? Left. Yeah, why don't we stiffen those up?
And I'm not good.
Okay. Yeah. Yeah, there's your carbons vertically fading away from you. See? So you don't point it like this. Turn it so the carbons are going away from you. These are in front. Carbons are in the back, these are in the front, and that's on the right. So that's Okay, so you want this up at the top. You wouldn't look at it like this with this down here. You would get this at the top. You would get these bottom 3 carbons in a line, vertical line, up and down, and fading away from you. Okay, so you wouldn't look at it like this with the carbons pointing towards you, because then this would be on the left, right? You want these things pointing away from you, and you want these 2 things pointing towards you.
Oh, okay.
Then you ask the question, where is that? It's on the right.
Oh, that's why it's D.
And that's D. That makes it D, because that is on the right.
Okay.
See, if it wasn't there, you'd have to break that and put it there. You can't just rotate this around and get it there. You can't just flip it over and say, oh, now it's on the right. Well, that's on the bottom. That has to be on the top.
Okay, so that carbon has to be pointing towards me. So I was thinking it was the
This
other.
carbon?
Yes.
Yeah, this carbon is kind of like right on the board. These are behind the board, and these 2 things are in front of the board. And now when you flatten that out, then you're going to get the Fisher projection with this on the right.
And didn't he say that those were
Yeah, that's the carbon carbon. It's any carbon that has 4 different things on it. 4 different things. We'll look it over. Yeah, that's better. Yeah, but now that's on the left.
Oh,
Okay?
Okay.
So move that over to there.
Okay.
And then get another stiff bond right in there.
okay.
Okay, let's take a look at this. Let's put our D-glyceraldehyde over here. All right, let me have your attention. Here is D-glyceraldehyde. And notice, this is your chiral carbon. Why is that? That has 1, 2, 3, 4 different things on it. This aldehyde group is not the same as that group right there. It's different. That's different from that. That's different from, they're all 4 different. So that's a chiral carbon. Now take a look at deerythros. This carbon here is chiral. It has 1, 2, 3. It has a CH2OH group here. And this thing is different from that. It's not a CH2OH, it's something else. That is not superimposable on that. So that's a chiral carbon. Well, if you went up here, you would find the same thing. If I had a different color, I probably could find one. But let me put these in squares. That, and that are all different. So that carbon has 1, 2, 3, 4 different things on it. So you go up to a 4-carbon monosaccharide and you get 2 chiral carbons in it. So this has a couple of different optical isomers. This would have more optical isomers. Now, I won't draw all over this glucose, but if you go to the glucose, now this is not a chiral carbon. Why? Why is this not a chiral carbon? It has 2 hydrogens. It has 2 things that are the same. It can only have 4 things, and if 2 of them are the same, it's going to have 3 different things on it. It's not chiral. You could spin that around and get these hydrogens to lay on top of one another, so that's not chiral. That is not chiral because it only has 3 things on it. It has a carbon, it has an oxygen, a hydrogen, and the rest of the molecule. There's only 3 things on that carbon. So the aldehyde is not chiral. But every one of these carbons in between is a chiral carbon. And the one from the bottom is on the right. This is just like, you can see that this portion of D-glyceraldehyde, this portion of D-glucose is just the same as this. That's why we're calling this D, because it's matching D-glyceraldehyde. All right, so this is the Fisher projection of D-glucose, or you could actually have this projection.
On the D and
Let me just finish this. If I came right down through here, and I just forgot about the carbons. And I got an OH, an OH, OH on the left, another OH on the right. That is, so I can either draw out all the carbons, or for a chiral carbon, I can just have a crossroads right there. There is a carbon there, but what's around it? There's an OH here, there's a hydrogen there. An OH, a hydrogen, OH, hydrogen. Yes, Samantha?
Going back to that one, which was that?
What, this one?
The chiral, yeah. Was that a chiral?
Here's a chiral carbon here and a chiral carbon there.
There's two chiral.
Two of them.
So there could be more than one. There could be 4 chiral carbons.
Yeah. Any carbon that has 4 different things on it.
4 different things?
4 different things. So let's take that one. Which one do you want to take? That one?
Yeah.
Okay, that one right there has a hydrogen and it has an OH. It has that thing, which is different from that thing. All right?
So you and my sets of 2?
Well, you just take each individual carbon and ask the question, does it have 4 different things on it? And if it does, it's a chiral carbon.
Can you do the one under so we could see the difference?
This one,
Yeah.
that, and that are different. This is different. It's got 3 carbons in it. That only has 2 carbons in it.
So you wouldn't just go down 1 carbon or up 1 carbon and over to your hydrogen and over to your, you would take the whole bottom section.
Yeah.
Bottom section from it.
I mean, if I had a molecule, if I could conceive of a molecule where I had a carbon like this, had this on it, and I looked up here, and what I had up here was identical to this, it wouldn't be a chiral carbon. Even if this was really pretty complicated. But I looked up there and it was identical. But I could tell this is not identical to that. That has an aldehyde in it, and this doesn't. Not identical.
So you're just taking the chunks of the top and the bottom of each thing and comparing?
Yeah. What you do, here's your carbon that you want to analyze. It's got 4 things attached to it. Every one of those carbons. So then you just say, what are they? There's 1. There's 2. There's what's attached to the bottom of that carbon. And there's what's attached to the top of the carbon.
How do you decide that's the carbon?
Well, that's the one I'm asking the question about. That would be, is that a chiral carbon? How do I figure it out? I look at what's attached to it. If they're all different, the answer is yes. Let's do it. Let's do a different one. Let's do this carbon. It has that attached to it. That's one thing. It has that attached to it, and it has 2 hydrogens attached to it. They're not different. So that's not chiral. I'm looking at this carbon. So forget these because I've drawn them here. That's not a chiral carbon. Why? Because it only has 3 different things. 1, 2, 3 different things. The 4th thing is not different. So to find out if a chiral carbon is, whether a carbon is chiral or not, you analyze that particular carbon. You look at that carbon and you say, what are the 4 things on it? All right, so glucose has 4 chiral carbons. And so you get to these Fisher projections. And here's D and L-glyceraldehyde. You see D, the OH is on the right. L, the OH is on the left. This is a perspective drawing of it. But here is the Fisher projection. In other words, we've smushed it flat into a 2-dimensional drawing. That's what we're doing with Fisher, is we're we're saying, okay, how are we going to put this in a textbook? How are we going to put this molecule in a textbook? We wouldn't put it in as a three-dimensional molecule, make a pretty thick textbook. So we're going to flatten it into a two-dimensional sheet of paper, and how are we going to do it? Like this, the way Fisher suggested. So this is his suggested way of drawing these things, and that's why they're called Fisher projections.
Professor, then if you said that glucose has 4 chiral carbons, can we use either one of them, or is there one specifically that we have to use? Or?
Yeah, there's one specifically we have to use, and you'll see this in a minute. So here's Fisher projections. These are Fisher, drawing the molecule with Fisher. You can see here, left the carbons off. You can just put what's on each side of the carbon. Yeah, and I'll say this again, but D-glucose is right, left, right. That's the pattern for D-glucose. Right, left, right. Going from the bottom up to the top. Right, left, right. That's D-glucose. Okay, so now let's look at these, and you tell me whether these are D or L. Here's 6 different saccharides, monosaccharides. What we're going to key in on is this carbon, one up from here, and ask ourselves that OH, take these all as Fisher projections. This OH is on the right, so it is D. This one, D. This one, this is an L. Okay? And all we're doing is focusing on this second carbon from the bottom. It does get more complicated than that as you would walk on up there, but that's as far as I need you to go right now. This slide is actually saying also then, is it an aldose or a ketose? Okay, what is this? Ketose. Aldose. I'm not asking you to name them, just what class do they fall into? Aldose. Ketose. Okay? And then, I mean, you could also go in there that you got a tetrose, triose, you got a hexose, I guess. Hexose, pentose, another hexose. So yeah, you could categorize all of these by number of carbons, aldehyde or ketone, and are they D or L. Okay, I said in the laboratory, chemically, they're going to behave almost identical. There's really no chemical test you can do, but there is a physical test. These isomers will actually rotate polarized light in different directions. And so you would use a fairly cheap instrument, actually, a polarimeter. You could probably get a polarimeter for $200 or $300, which is a relatively cheap laboratory piece of equipment. And here's what that would look like. Here's what that would look like. So what you would, this is a light bulb. I can see it better on my screen here than I can see it there. But there's a light bulb just emitting the complete spectrum of light. Here's a polarized filter like you would have in a polarized lens in a glass. And what's that doing? Wavelengths of light are coming at this lens or this filter right here, and they're vibrating. They're in all different kind of directions, 360 degree directions. The polarized filter will let only the light beams that are vibrating or oscillating in a certain vertical pattern through the polarized filter and filter everything else out. So now you have polarized light. And right here would be a little container like a test tube or a cuvette of some sort with your glucose in it. Put your glucose in there, in water. It's in a solution, passing polarized light through it. And the polarized light coming through the glucose of one particular isomer will get rotated. The oscillation will get rotated a little bit, and the polarimeter will detect that and say, okay, it's rotating the polarized light to the right or to the left of its original orientation. And you get that. So a mixture of D would rotate it one direction, L the other direction. You'd be able to tell the difference. If you extracted the glucose from the leaves out there, you'd find, oh, it's all D, glucose. So that's the only property in the laboratory that I know of where you could distinguish D from L. But your body will only metabolize D. And that goes for all the saccharides. The body is using D. So they're saying, and that's interesting, that L-lactic acid is found in living muscles. So when you exercise hard and you metabolize differently, you're producing lactic acid, and it's producing L-lactic acid. I find that, I'm just kind of struck by that. Because one thing I learned recently here is that cancer cells will prefer that metabolic pathway, and they'll produce lactic acid. Cancer cells excrete a lot, and I'm wondering if it's L-lactic acid. That never came up. Never came up in what I was studying, what isomer it was. But, all right, so D-lactic acid is found in sour milk. But in generally speaking, all of the saccharides are D. D-fructose, D-lactose, D-glyceraldehyde are the biologically active saccharide. All right, so here's your D-glucose. Right, left, right. That arrangement. Okay, now here's a decent slide, and this will get you to some 3x5 cards that you can take note of, forget about until after the test tomorrow, and then over the weekend have something to do, which is learn these. Not all of these. These are all D. Notice, they're all D. Right. These are all D monosaccharides. All right. A 3-carbon monosaccharide only has one chiral carbon. That's glyceraldehyde. There are 2 enantiomers. There's D-glyceraldehyde and L-glyceraldehyde. This slide is just picking up the biologically active monosaccharide. This exists in your body. Your body makes and uses D-glyceraldehyde. So this is one that you should memorize the structure of. And you could either draw it like that, or you could, you could just draw it like this. Those are both D-glyceraldehyde. This is probably a good way of drawing it. If you go up to 4 carbons, we've already been showing erythrose. It has 2 chiral carbons, so you can get, for D-erythrose, you have to have this on the right. So in both of the versions of the 4 carbon, you're going to have an OH on the right, but you can have the other one on the right, that's erythrose, or you can have the other one on the left, and that's threose. You don't have to memorize either one of those. Okay, jump up to 5 carbons long. 5 carbons long. There are 3 chiral carbons. When you get to 5 carbons long, D-ribose, right. They're all on the right. And that is one I want you to memorize. Where does this sugar show up? Where?
RNA.
RNA. What does RNA stand for? Ribonucleic acids. What does the ribo stand for? It's got ribose sugars as the backbone. All right? So that's a sugar you need to learn. Ribose. And it's right. This is how you're going to memorize these. Where are the OHs on these 3 chiral carbons? They're all on the right. That's ribose. And that's the only one of those you have to memorize. So you could have right, left. That's arabinose. Right, left, that's xylose. Right, left, that's alixose. Okay, now that's 5 carbons. Now you get up to 6 carbons. 6 carbons. And you got 1, 2, 3, 4 chiral carbons. You got a whole lot more options. Obviously, you're going to need to memorize D-glucose. And it's right, left, right. And the only other one here is going to be D-galactose. Right, left, right. So it's very similar to this one. You just gotta move one over there. Right, left, right. It's galactose. So there are 4 monosaccharides that you should be able to draw. Fisher projections with the OH groups in the right place.
Yeah. The one number 4?
Just ribose. Which? Over here, you mean?
I'm 4 carbons. Nothing on them.
This one, ribose.
Okay, but that's 5 carbons.
Oh, 4 carbon. Nothing. Yeah, you're right. I'm sorry. I'm sorry. The 4, you don't have to memorize the 4. Glyceraldehyde, ribose, glucose, galactose, and then the other one is not an aldose. See, these are all aldoses. Fructose is a ketose. And so if you want to write down here, also memorize fructose. And I think that's it. There's 5 monosaccharides. I think I got an idea. It's dangerous, but I'm always thinking. Downright dangerous. As soon as they outlaw that, the world's going to settle down. I think what I will do, I think this is far enough for chapter 13, or chapter 16, the biochemistry. Like I said, tuck that away, and after the exam, we'll pick back up on, we'll finish chapter 16 and start chapter 17 after the exam tomorrow. So let's shift over, talk a little bit about the exam. I will actually grade chapter 15 homework while you guys are reviewing, checking things out, figuring out what questions you have, and so about maybe 10 to 2 or so, I'll get these done graded, and then we'll answer some questions. We'll review that reaction summary for chapter 13, 14, and 15, and any questions you have. Pardon me?
How much time are we going to have
For the test, probably an hour and 15 minutes. Let me mention this about the test.